So the Unit 6 test is a pretty long one. There's 10 different learning objectives, so the test is going to be a little long, but there's kind of one big main idea, which is the effect that derivatives have on graphs, and then there's a couple other small things related to the mean value theorem and the extreme value theorem in there. All right, so I'm going to break it up. This video will do the first 3 learning objectives. So in this one, we're talking about using the mean value theorem. Or the mean value theorem, the function needs to be continuous and differentiable. And then when that happens, that means there's a tangent line that's parallel to the secant line. All right, so that's the important thing to remember for the mean value theorem. So for this first one, all right, it says we have this function that's continuous. F of -2 equals f2, and they are both 0. So if I plug in -2, I get 0. If I plug in +2, I get 0. So the secant line between them is also going to have slope 0. And the question said there's no c where f prime of c equals 0. So that means the mean value theorem is not true, right? Because if the mean value theorem was true, there'd be some c where this tangent line is parallel to that secant line. So what's the only reason when the mean value theorem won't work is if we don't satisfy the initial conditions of the mean value theorem, which is to be continuous and differentiable. All right, they tell us it's continuous, so that means at some point it has to be not differentiable. So at some point, the original function does not have a derivative, which is exactly what D says. All right, at some point, f prime of k, which is the derivative, does not exist. All right, so that's the only time the mean value theorem won't work, is if the derivative doesn't exist at some point, all right, or it's not continuous. But they tell us it's continuous, so it has to be that the derivative does not exist. All right, the following table gives selected values for the continuous and differentiable function. All right, which of the following must be true? All right, A, the minimum value of f is 2. We see 2 is the smallest value in the table, but we don't know what's happening in between 0 and 1. All right, it could go down farther before it goes back up to 3. All right, so A is out. The maximum value is 4. We see 4 is the biggest number in the table, but for the same reason, 4 could be here, and it could go up and then back down before it comes back to 3. So for the same reason, B is out. All right, f prime of x is less than 0 between 2 and 4. All right, so from 2 to 4, we see it goes 4, 3, 2, which means it's decreasing, which means the derivative is negative. But again, for all the same reasons, we don't know what's happening between 4 and, or that 4 value and that 3 value. It could go straight down and be decreasing, but it could also go up and back down. So we don't know the derivative is negative for everything. And D, there exists a c between 0 and 4 where f prime of c equals 0. So this is the slope of the tangent line, the slope of the secant line. It starts at the y value 2 and ends at the y value 2, so the slope of that line is also 0. All right, so the mean value theorem says that D should be right. And again, we eliminate all the other ones, so it has to be right as well. All right, for number 3, selected values for the function f are given below. What is the fewest possible number of values of c, which f prime of c equals 6? And it says we're using the mean value theorem, so remember, this is the slope of the tangent line. So if we find the slope of a secant line that's also 6, that guarantees from the mean value theorem that it has to be true. So we just have to think about all these different secant lines that can happen. All right, so there's going to be a lot of different combinations. We can go from 1 to 3. All right, so 1 to 3, the secant line, we do the y values over the x values, and that's 3. All right, so that one doesn't work. All right, we could do 1 to 5. Get the difference in the y value is 18 over 4, which is definitely not 6. 1 to 7 is 29 over 6. That's definitely not 6. 1 to 9 is 42 over 6. 42 divided by 6 is 7, which is not 6. All right, so none of those work for 1. All right, then we could do 3 to 5. The difference in those y values is 12 over 2, and that is 6. All right, so now we have at least one place where our secant line has a slope equal to 6. We could do 3 to 7. It's going to be 29 minus 6 is 23 over 4, and that's definitely not 6. 3 to 9. 42 minus 6 is 36. and the difference 3 to 9 is 6. 36 over 6 is 6. All right, so it looks like we have another place. And let's see, 5 to 7. Difference in those ones is 11 over 2. That's definitely not 6. 5 to 9. The difference from 5 to 9, 42 minus 18 is 24 over 4. And that's 6. All right, so now we have another one. And the only one we haven't checked yet is 7 to 9. 42 minus 29 is 13, or a difference of 2, and that's definitely not 6. All right, so those are our 3. Let's just double check the 3 that we think. All right, 3 to 5, the difference in the x values is 2. 18 minus 6, the difference in the y value is 12, so 12 divided by 2 is 6. All right, so this one definitely works. All right, 3 to 9, 42 minus 6 is the difference in the y values. The difference in the x values is 9 and 3, so that's 6. So 36 divided by 6 is 6, so that one definitely works. And lastly, 5 to 9, 42 minus 18 is 24. Our difference in our x values is 4, so 24 divided by 4 is 6. That one also works. All right, so our final answer should be 3. Oops. And the last one, the mean value theorem in your own words. All right, it should be something like this. Again, it's in your own words, so it might not be exactly right, but if f is continuous, the specifics are it's continuous on the closed interval and it's differentiable on the open interval, then there is a tangent parallel to the secant line from x equals a to x equals b. All right, something like that. All right, first of all, you have to know the conditions. It has to be continuous and has to be differentiable. All right, and then there's some type of tangent line you can find that's parallel to the secant line. All right, our next learning objective is about the extreme value theorem. All right, so first question, which of the following functions of x is guaranteed to have an absolute max and min? All right, so the conditions of the extreme value theorem is our function has to be continuous. All right, and then if it is continuous, it says there is an absolute max or min. So for this one, if we want to guarantee it has an absolute max or min, then all we have to do is make sure it's continuous. All right, all of these functions are fractions, which means if the bottom of the fraction is 0, then I'm not going to be continuous because you'd get an asymptote or a whole. All right, this bottom, 1 plus sine of x, if I plug in sine of 3 pi over 2, I get -1, and that would make the bottom 0, so this one is out. All right, this one, if I make x pi in either of these two, I get 0 on the bottom, so those are out. The only one that's going to work is b, because x squared plus pi is never 0. The next one, we have f is a function with the selected values in the given table. Which of the following must be true? All right. So all these kind of fit. If you go through the immediate value theorem, that kind of makes sense. The mean value theorem, the conclusion kind of makes sense. Extreme value theorem kind of makes sense. All right, but all of these theorems that we've learned require f to be continuous. And you notice what they give us, they just said f is a function. They don't tell us anything about continuity or anything like that. So they don't give us the thing that we need to be able to use these theorems. So a is out because we can't use that. B is out, we can't use that. C is out, we can't use that. So the only option for the right answer is that none of them work. Right. If they put continuity up here, then A and C will be right because those just require continuity. B wouldn't be right because the mean value theorem also requires differentiability. Right? But since they don't tell us continuous, none of these can be right. Right, here we have this point P. Right, what do we know about P? Basically, we're looking at absolute and local max and mins. All right, so the first question, is P an absolute max And the answer is no, because absolute maxes are the biggest thing in the entire graph, and there's all these values up here that are bigger than p. So anything that says p is an absolute max, and an absolute max, not an absolute max, not, okay. So A and B are out because p is definitely not an absolute max. All right, what about being a local max? Local max just means that it's bigger than everything around it. So we just kind of put a small box around p. All right, and that small local area, is p the biggest value? And yes, it is. It's at the top of that small hill, so it is a local max. So it's a local max, but not an absolute. So C is the right answer. And last one, just like the last one, you have to state the extreme value theorem in your own words. Again, make sure we know the one condition that if f is continuous on this interval, right, then f attains a maximum and minimum. All right, and again, the precise words aren't super important, but as long as you're saying f is continuous, all right, that's one of the most important parts. All right, f is continuous, that's our assumption we have to have. And then if it's continuous, then you're going to get a maximum value and you're going to get a minimum value. All right, but again, in your own words, explain what that theorem means. Our third learning objective has to do with the first derivative and our function being increasing or decreasing. All right. So first one, we have this derivative. A is positive, constant. All right, which of the following statements is true? So the derivative itself is going to tell us about the original function. Don't have to take a derivative in this problem, but I want to figure out when the derivative is positive and negative, because that's going to tell me increasing and decreasing. So I need a number line. And I start out with the places where my derivative is 0, which is going to be a and negative a. Right? I could plug in a there or negative a there. If I'm to the left of negative a, so let's just pretend this was like 2. If I'm to the left of negative 2, if I plugged in like negative 3, this would be negative 3 minus 2, which is still negative. Negative 3 plus 2 is still negative, so those negatives cancel and give me a positive. In between negative 2 and positive 2 would be 0. If I plug in 0, I'm going to get a negative times a positive, which is L, that's negative. And if I had it something bigger than a, like 4, 4 minus 2 is positive, 4 plus 2 is positive, so everything is positive. So when is this decreasing? All these answers have to do with decreasing. So when is this function decreasing? Between negative a and a. And the only one that satisfies is a. All right, so a is the right answer, because in that middle region, my function's decreasing. All right, next one, when is my function only increasing? Well, again, we have to use the derivative, but here they give us the original function. So the first step is to take the derivative. That's going to be x squared minus 8x plus 15. All right, just like the previous problem, we're going to make this number line. So we start off with when is it 0? All right, so we figure out that the answer is 5 and 3 is when it's 0. So now when we make our number line, we'll put 3 here and 5 here. And we'll figure out our test points. So we could do 0, 4, and 6. Again, test points, just any number that's in that region. The only thing I would say, if you could plug in 0, always plug in 0. So if I plug in 0 into this derivative, I'm going to get 15. And I want to plug it into the derivative because I want to know if it's increasing or decreasing. If I plug in 4, I'm going to get, so I'm actually going to plug it in here to the factored form because that's easier. 4 minus 5 is a negative number. 4 minus 3 is a positive number. A negative and a positive make a negative. And 6 minus 5 is positive. 6 minus 3 is positive, so everything's positive. All right, so when is it only increasing? 0 to 4 would be from here to here, and it kind of crosses the interval, so it's not only increasing in that interval. All right, so that's out. 3 to 5, it looks like it's decreasing, so that's out. 4 to 6 would cross between these intervals, so that's some decreasing, some increasing, so that's out. 6 to 10 is just in this far right-hand interval, so that is our final answer. All right, so our final answer is 6 to 10 is when it's only increasing. That be a function that is increasing if x is less than 2 and decreasing if x is bigger than 2. Which of the following could be true? All right, and we're all related to the derivative. All right, so remember, if the function is increasing, that means f prime is bigger than 0. If it's decreasing, our derivative is less than 0. All right, so 0 is to the left of 2, so I should be increasing. All right, so my derivative should not be negative. It should be positive. All right, so B is going to end up being the right answer, but let's look at why the other ones aren't right. All right, 4 is bigger than 2, so I should be decreasing, but both these are positive answers, so that's why those are not right, and B is the only one that makes sense. All right, so now we're going to sketch a graph that is the derivative is less than 0 if x is less than negative 2, so that's negative 2 is going to be right there. It's 0 if x is between negative 2 and 1, and it's less than 0 after that. So remember, if the derivative is less than 0, I'm decreasing. So as long as my function is going downward in any way to negative 2, then that means my derivative is negative. If my derivative is 0, there's only one possible thing you can draw if your derivative is 0, and that's a flat line. That can't be increasing or decreasing, so it has to be a flat line. Then after that, it's decreasing again. I mean, you can just draw straight lines. You can do little wiggly lines as well. All right, but that is a function that satisfies it. All right, the easier way probably is to use straight lines. So straight line down, flat line, straight line down. All right, and the flat line doesn't have to be where I drew the flat line, or it could look like this as well. All right, straight line down, flat line, straight line down. All right, all those satisfy this conditions.